This section has a lot to cover. We're going to spend a good bit of time on area and polar coordinates. So in order to do that, we'll need to practice sketching polar graphs. We'll find the area inside a polar curve, the area inside one polar curve but outside of another, the area inside of two polar curves at the same time. In order to do that, we're going to need to find intersection points. We'll also compute arc length, that's the easiest piece. We'll find the tangent to a polar graph. It's very similar to what we did with parametric, as is the arc length. So let's start with area. The way we do it is we think about the area of a sector of a circle, which you learned way back in pre-calculus trig. So the area of a sector of a circle is 1/3 r squared theta, radius times the measure of the sector. So this area of a sector is proportional to its central angle. So we take the polar graph and divide it into sectors, and then we let the number of sectors approach infinity, which sounds like an integral, and yes it is. So we end up with that formula for the sector, 1/2 of the radius squared. Well, the radius is the function, so it's 1/2 of the function squared. As we go from A to B, the radian measures. Let's look at an example. We want to find the area enclosed in one loop of the four-leafed rows, r equals cosine 2 theta. So you need to know how that four-leaf rows is created so you can figure out the limits of integration to find the area enclosed by one loop. So you need to remember, first off, that if you have r equals cosine 2 theta, it's a rows because you have cosine or sine, your trig function, with a number sitting next to theta. It's an even number, so you have 4 petals on your rows. Even coefficient implies 2 times, and let's give it a name, even coefficient A implies 2A petals. And if you remember, that means since it's cosine, your first petal is going to live on the x-axis. But I'm going to go ahead and write down my little chart that I create. I make a column for theta and a column for r. Now, my norm when I'm creating a polar graph is to look at 0, pi halves, pi, and 3 pi halves. But I have this coefficient sitting next to theta. When I have a coefficient sitting next to theta, I take my big 4, which is what I call them, and divide them by this number. So I'm going to start, instead of 0, pi halves, pi, and 3 pi halves, I'm going to start by plugging in 0, pi over 4, pi over 2, and 3 pi over 4. So I divide each of these by that coefficient. And then if I need to expand my table, I will, if I don't get enough to know what my graph is going to look like from there. So I plug in 0. I have cosine of 2 times 0, which would just be 1. So we'll put 1 right here. I plug in pi over 4, I get cosine of 2 times pi over 4, which is pi halves, which is 0. So by the time we get to pi over 4, we're already back to 0. I plug in pi halves, would be cosine of pi, which is -1. So at theta equals pi halves, we flip to -1, which is down here. And then at 3 pi over 4, I'm at cosine of 3 pi over 2, which is back to 0. So I'm back to here. So I know how my graph is being created. As theta goes from 0 to pi halves, I've drawn this top half of this loop, of this petal. So since I'm interested in the area enclosed in one loop of the 4-leafed rose, I could find 2 times the area that's drawn from 0 to pi over 4. One half cosine 2 theta squared d theta. I could have computed the area from here where it's 0 pi over 4 to 3 pi over 4 and found the area of this loop. I could have taken the area from negative pi over 4 to positive pi over 4 and found the area of that whole loop. But since the petals are symmetric, I can just double that integral from 0 to pi over 4. And there's the pretty picture. I wrote it as negative pi over 4 to pi over 4 there. And then since it's cosine squared, you know you have to use that double angle formula. On this particular test, I'll actually let you just plug it in your calculator. But we end up with pi over 8. So give this one a try. You can actually tell exactly what your limits of integration are going to be just from the picture on this one. So give it a go, see how it goes. Okay, I went ahead and drew my own graph because that helps me to see how the polar graph is drawn and what I need my limits of integration to be. Because remember, polar graphs are drawn in a sweeping motion from the polar axis around counterclockwise. So the shaded region happens from pi over 2 to pi. Then I went ahead and I did this one by hand because I had plenty of time. And I ended up with 9 pi over 8 minus 2. And if WebAssign wants an exact answer, then that's what you're going to need to do. So now this one, you have to sketch it and figure it out yourself. So sketch the curve and find the area it encloses. So you need to figure out how long the period is to draw that curve so you'll know what the limits of integration are. This one was a lot like integrating the last one, except it was 2 minus cosine theta instead of 2 plus cosine theta. So it was the area of the whole thing. It took from 0 to pi to integrate it, and we end up with just 4 pi. Find the area of the region enclosed by one loop of the curve r equals 2 sine of 5 theta. So it's similar to what we did back here on example 1, except think about the fact that we have an odd number of petals, and you're going to have to figure out how long it will take you to create one loop of that curve. So divide your big 4 by 5 and figure out what your limits of integration need to be. So I started drawing this one, and just because I wanted to confirm for myself that when I have an odd number of petals, I draw the whole thing, the entire rows, on the interval from 0 to pi, I went ahead and did it again. Instead of just looking at the big 4, I kept going until I got all the way around to pi, but I only needed this one loop here. Now, if you want to, do some exploring, you can use Desmos, which I plugged it into Desmos. And if I just go from 0 to 3 pi over 10, I get this extra little loop here. In order to get the first loop, I only needed to go from 0 to pi over 5. That gave me my first little loop there, and it creates the whole rows on the interval from 0 to pi. If you have an even number of petals, then you can see it. You don't get the whole rows as you go from 0 to pi. You need to go all the way from 0 to 2 pi to get all 8 of the petals when you have an even number. Okay, so let's bring back example 2. So now we're going from just inside of one curve to inside of one but outside of another. So we want to find the area that lies inside the circle, r equals 3 sine theta, and outside the cardioid, 1 plus sine of theta. Now on test day, I won't give you the points of intersection like this graph does. So let's compute those. Example 2, let's set 3 sine theta equal to 1 plus sine theta. So we'll subtract a sine theta from each side. 2 sine theta is equal to 1. So sine of theta is 1/2. And the cardioid takes the interval from 0 to 2 pi in order to draw it. The circle, 3 sine theta, is drawn completely over the interval from 0 to pi, but we get 2 intersection points in that interval from 0 to pi because sine is equal to 1/2 on the top half of the unit circle at pi over 6 and 5 pi over 6, just like the picture says. So we need to find the area that's inside the cardioid but outside of, inside the circle and outside of the cardioid. So remember, as we draw this picture, I'll do a little quick picture. Let's see, it's 1, 2, 3, and it's sitting above, and then my cardioid is here, and it crosses the axis up here at 2. So something like that, and we're looking for this piece. So these graphs are drawn in a circle this way. So it's going to start here, and as it sweeps over, this will be on the outside, and then we'll subtract off this piece that's on the inside. Now you could go all the way from pi over 6 to 5 pi over 6, or you can just find the area from pi over 6 to pi over 2 and double it. And I'm going to do that. Pi over 6 to pi over 2, and I'm going to double it. And then we have 1/2 on the inside, because that's part of the formula. We have our outside, and the outside is 3 sine theta squared, minus my inside is my cardioid, and my cardioid is 1 plus sine theta squared d theta. And then we have some squaring to do, and we end up with pi for our final answer. I won't go through all of the integrating on that one. So here's your practice problem. Find the area that lies inside the first curve and outside the second. So we're going to have to draw our own picture on this one. We'll do this one together. So we have r equals 3 cosine theta. So let's sketch that first. We have theta, and we have 3 cosine theta. I'm going to start just going from 0 to pi halves to pi. Three times cosine of 0 is 3. 1, 2, 3. 3 times cosine of pi halves is 0. So we've circled up and gone to 0. At pi halves, I have 3 times cos of pi. I have 3 times cosine of pi, which would be -3, and that brings me back around to close my circle. So this circle lives to the right of the y-axis. Now let's see what 1 plus cosine theta looks like. So theta and 1 plus cosine theta. So I have 0, pi halves, pi, 3 pi halves. 1 plus 1 is 2. 1 plus 0 is 1. 1 minus 1 is 0. And 1 plus 0 is 1. So 2, 1, 0, 1. This is a cardioid, and it shouldn't look quite so much like a heart as I've drawn it. So I'm going to erase and try to make it look a little better. Yeah, my picture doesn't look that much better, but I tried. I'm not good at drawing. I do the best I can. So we want the part that is inside of the circle, but outside of the cardioid. So I'm looking for this piece. But again, I'm just going to go from here to here and double it. So I need to know what this point is. I set 3 cosine theta equal to 1 plus cosine theta. So we're getting a head start on that finding the intersection points goal. 2 cosine theta is equal to 1. So cosine of theta is equal to 1/2. So theta is equal to, and over here we would have pi over 3. If I wanted to start down here and do my integration, I would need to go from negative pi over 3 to pi over 3. But I'm going to double it. So my area is equal to 2, integral from 0 to pi over 3, outside squared. Oh, don't forget the 1/2. That's part of the formula. 3 cosine theta squared minus 1 plus cosine theta squared d theta. Now I'll take a break and do the integrating, and we'll meet back and compare answers. Well, I worked kind of hard for it, but I ended up with pi. I took 3 cosine theta, squared it, subtracted off the square of 1 plus cosine theta, combined like terms, used the half angle formula, and ended up with pi. Now, inside both curves, I think these are the most challenging. We want to find the area that lies inside both curves. So when you're finding what lies inside one and outside the other, it's kind of like the area between two curves in Cartesian coordinates, because you're doing an outside minus an inside. When you're doing inside two curves, there's more logic to it, and you have to really draw the picture. So let's draw the picture. And this is inside both curves, practice A. Inside both. So we have r equals 3 sine theta and r equals 3 cosine theta. So let's sketch those first. Well, we kind of know what it looks like, but I'm going to go ahead and draw my little table. Theta and r. I know it's drawn completely from 0 to pi. So theta is equal to 0. I'm at 0. Pi halves, I'm at 1, 2, 3. And then at pi, I'm back to 0. So here's my little circle, kind of like a circle, that lives above the axis. And then for r equals 3 cosine theta, we know exactly what that looks like. We drew it a moment ago. It starts at 3, so theta and r, 0, pi halves pi. It starts at 3, and then at pi halves it's at 0, and then negative 3. This one's 3, 0. So here and around. Now it looks like it's going to cross right there at pi over 4, so let's just confirm. 3 sine theta equals 3 cosine theta. Well, that means sine theta over cosine theta. Tan theta is equal to 1, so theta is pi over 4. So we're looking for this little kind of a football shape right here. I can't find the area of that little shape by doing one minus the other, because it's the area inside of the sine during this little piece here, and it's the area inside of cosine in that little piece. So you have a choice. You could find the area of this piece and then add it to the area of that piece, or you could find the area of either of those pieces and double it. I'm going to go with what I think is easiest, and that's just to find the area of this little football right here. So the area is equal to 2, integral from 0 to pi over 4 of the sine curve. 0 to pi over 4, 1/2 of 3 sine squared theta d theta. And actually, I'm going to put the square on the outside because that 3 gets to be squared as well. Now let's take a moment and look at that on Desmos. I'll get rid of the old stuff. I put in r equals 3 sine theta, r equals 3 cosine theta. And I want this little football right here. So let's look at r is less than 3 sine theta, going from 0 to pi over 4. See, that's that first little half of a football. Let's make it or equal to, so I don't have those dashed lines there. So this is the area that I'm finding. I could add to it r is less than or equal to cosine theta, 3 cosine theta, from pi over 4 to pi. That's the other little part of the football there. So you have to kind of get used to where these things are drawn. So we could add up either of those and get the right answer. And now I'll take a minute and do the integration and come back with an answer for you. I've done the half angle formula a few times today already, so I just kind of did it in my head. 1/2 of 1 minus sine of 2 theta. So I pulled the 1/2 out. The 9 hung out because 3 squared was 9. Integral of 1, integral of sine or cosine of 2 theta, sine of 2 theta over 2, and then I just plugged in 0 to pi over 4. Okay, try this one on your own. You're going to have to draw 3 plus 2 cosine theta and 3 plus 2 sine theta and find the area that lies inside both curves. So sketch them, see where they cross, and probably it'll be something symmetric that you can double. We'll see. Got to admit, I think I did a pretty good job of sketching these two things. But beside the point, I drew 3 plus 2 cosine theta, which is a dimpled limacon, which lives on the x-axis. And then 3 plus 2 sine theta, a dimpled limacon that lives on the y-axis. I figured out that they cross at pi over 4 and 5 pi over 4. So if I'm going to draw this piece, it starts at negative 3 pi over 4 and goes up to pi over 4 on the sine limacon, and then this one starts at pi over 4 and goes down to 5 pi over 4 on the cosine limacon. So you could have added those two things together. I just doubled the cosine limacon, and let's look at the pretty picture. So first you could just graph the two and see where they cross. They cross here at pi over 4 and 5 pi over 4. If you look at just the cosine piece from 5 pi over 4, from pi over 4 to 5 pi over 4, that gives you like the top half of that little lemon. And then the sine gives you the bottom half of the little lemon. So use Desmos to explore these things and get used to them, and that's going to help you. Okay, let's practice finding some points of intersection. We've already been doing it, so we won't have to do a lot of examples because we've already done some. Anytime you're looking for points of intersection, you always want to check the pole. Now, example 3, we want to find all points of intersection of r equals cosine 2 theta. This is example 3. And r equals 1/2. Well, r equals 1/2 is super easy. That's just the circle at the origin whose radius is 1/2. So I'll just go ahead and try and draw that. We'll call this 1/2. This is a 4-petaled rose whose first petal lives on the x-axis and has length 1. But if you don't remember that, then you would do your theta and r. You would take your big 4, 0, pi halves, pi, 3 pi halves, divide them by the number sitting next to theta, and you would start sketching with 0, pi over 4, pi halves, and 3 pi over 4. And then you would have cosine of 0 gives you 1. Cosine of 2 times pi over 4 is pi halves. That brings you back to 0. Cosine of pi halves times 2 is cosine of pi, gives you -1. So when theta is equal to pi halves, which is what we plug in here, we're at -1 right down here. At 3 pi over 4, we're back to 0. If I went ahead and finished, the next one I would plug in would be pi. That would bring me right over here to 1. And then I would be back to 0, up to 1, and back to 0, and then to -1. So I can see that there are 1, 2, 3, 4, 5, 6, 7, 8 intersection points. The pole is not one of them because the circle doesn't go through the pole, so that's not a problem on this one. Let's set these equal to one another. Cosine of 2 theta is equal to 1/2. So that means 2 theta is equal to, well, cosine's equal to 1/2 when we have pi over 3 plus 2 pi k, or 2 theta is equal to, let's see, we're positive in the first and in the fourth quadrants, so pi over 3 and 5 pi over 3. Then I divide everything by 2. So I get pi over 6 plus pi k, and I get 5 pi over 6 plus pi k. So from this one I get pi over 6, add another pi to it, 7 pi over 6, add another pi to it. Well, if I do that, I get 13 pi over 6, which is bigger than 2 pi. So I've gotten 2 answers from here. I have 5 pi over 6. I add pi to it. I get 11 pi over 6. If I add another pi, then I would have 17 pi over 6, which is bigger than 2 pi. So I've only gotten 4 answers by solving this. So either you have to think about the symmetry. We found half of the answers. We could find the other half by looking at the other things that have 6 in the denominator. My other option is to realize that r equals negative 1/2 has the exact same graph as r equals 1/2. If I solved this, then I would get 2 theta is equal, cosine of 2 theta is negative 1/2. And then I would get the 2 pi thirds plus 2 pi k, and I would get 2 theta is equal to 4 pi thirds plus 2 pi k. And that's how I would get the other answers, which would be 2 pi over 6 4 pi over 6 and pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So you have to really think about it and work for these answers sometimes. So let's practice. 1 plus cosine of theta and r equals 1 minus sine theta. Told you we were going to get lots of practice sketching these curves. So let's look at 1 plus cosine of theta and 1 plus sine of theta. Practice. Intersection. Set them equal to each other first. So 1 plus cosine theta equals 1 minus sine theta. Subtract 1 from each side. Cosine of theta is equal to the negative of sine theta. Well, either you divide and think about tangent, or you just think about your unit circle. You know that's going to be where cosine and sine have opposite signs, and where they have 4 in the denominator. So 3 pi over 4 and 7 pi over 4. But we have to think about, do these two graphs go through the pole? So what does 1 plus cosine theta look like? Now, I'll do a tiny little chart over here. I have theta, I have r, 0, pi halves, pi, 3 pi halves, 1 plus 1 is 2, 1, 0, 1, 1, 2, 1, 1, 0. I have a little cardioid. 1 minus sine theta, I'll do a little chart over here. 0, pi halves, pi, 3 pi halves. At 0, we're 0. Actually, at 0, we're 1 minus 0. So we're at 1. At pi halves, we're at 1 minus 1. That's where we're at 0. At pi, we're back at 1. And then at 3 pi halves, we're at 1 minus negative 1, which is 2. So we'd be down here at 2. So we start at 1. So we intersect over here. We intersect right here, but also at the pole. So at 3 pi over 4, 7 pi over 4, the pole. And we actually need to have our polar coordinate here. So we need an r theta. We have the theta. We just need the r. So at pi, 3 pi over 4, it would be 1 plus cosine of 3 pi over 4, which would be 1 minus square root of 2 over 2. And at 7 pi over 4, cosine is equal to positive square root of 2 over 2, so it would be 1 plus square root of 2 over 2, 7 pi over 4. So that's our polar coordinates of the intersection points. You could figure out the Cartesian coordinates if you wanted to. Let's look at a pretty picture of it. And here's my two curves. We have 1 plus cosine theta. That was the cardioid that lived on the x-axis. We have 1 minus sine of theta, the cardioid that lived on the y-axis. And then I did r cosine 3 pi over 4, r sine 3 pi over 4. That gave me this point because Desmos doesn't plot polar coordinates, it plots Cartesian coordinates even when you have a polar graph up there. And then we had r cosine 7 pi over 4 and r sine 7 pi over 4. So that gave me my two intersection points. Okay, try the next one on your own. We'll meet back and compare answers. Okay, my picture's terrible. It's just really terrible. Those don't look like roses. Those look like wilted roses. But it does show me that they have 1, 2, 3 intersection points. I ended up with 1, 2, 3 intersection points plus the pole, and of course the pretty picture. So the purple one is the sine rose because its first petal lives in the first quadrant. The second, the green one, is the cosine. Its first petal lives on the x-axis, and they're drawn on the interval from 0 to pi. Okay, arc length. To compute arc length, we think of our x is r cosine theta and y is r sine theta, and view it like a parametric set of equations. So let's do that. So x equals r cosine theta, just like when I was graphing those points a moment ago. Y equals r sine theta. So that means if we are using the product rule, dx d theta would be equal to dr d theta times cosine theta plus the derivative of cosine, which is negative sine. So just r times negative sine theta. And then this is dx d theta, not dx dx. Then dy d theta would be equal to dr d theta. Derivative of sine is dr d theta times sine of theta plus r times the derivative of cosine of sine, which is cosine. Okay, so now we have dx d theta, dy d theta. What we want to do is square them and add them together so we can use the formula for arc length that we learned back in the parametric section. So we need the square root of dx d theta squared plus dy d theta squared. So dx d theta plus dy d theta squared. So I square this. I have dr d theta squared cosine squared theta minus, and I'm going to run out of room, so let's just look at it where I have it typed up already. So I square the first term, 2 times the first times the last, so I have 2 times dr d theta cosine theta times r sine theta. So that gives me minus 2r dr d theta sine theta cosine theta. And then the last term squared, r squared sine squared theta. Then same thing for this one, r squared dr d theta squared times sine squared theta. And then we have 2 times r cosine theta times dr d theta sine theta. And then the last term squared. Okay, so let's see what we have here. We have 2r dr d theta sine theta cosine theta plus and minus, so that goes away. I have dr d theta squared times cosine squared theta, dr d theta squared times sine theta. So let's just take this. We'll leave out that first line that I was looking at. We already know that these two things undo one another. So I have dr d theta squared times cosine squared theta plus dr d theta squared times sine squared theta. I also have r squared sine squared theta and r squared cosine squared theta. So I have the derivative squared times cosine squared plus sine squared. And I have r squared times cosine squared plus sine squared. But cosine squared plus sine squared is 1. So I really just have dr d theta squared plus r squared. That gives us our formula for arc length. So length from A to B, the integral from one end to the other, square root of r squared plus dr d theta squared. So we want to find the length of the cardioid. We need to know how long it takes us to draw that cardioid. Well, the period for a cardioid is 0 to 2 pi. Zero to 2 pi, square root r squared, which would just be 1 plus sine of theta squared, plus dr d theta squared. The derivative of 1 plus sine would just be cosine squared of theta d theta. There's the pretty picture. So we end up with the integral from 0 to 2 pi of just 2 plus 2 sine theta. And I wouldn't expect you to integrate that by hand, but it's equal to 8. Okay, let's try one where we have to do an exact arc length, which means you have to integrate by hand. So, practice. R is equal to 5 to the theta. Now this one we're given our limits of integration. because r equals 5 to the theta is a spiral, I believe. I'll graph it in a moment and we'll check it out. But this arc length would be the integral from 0 to 2 pi square root of r squared, which would be 5 to the theta squared, plus the derivative of 5 to the theta, which would be 5 to the theta times the natural log of 5 squared d theta, which would be integral from 0 to 2 pi square root of 5 to the theta squared times 1 plus the natural log of 5 squared d theta, which would be 0 to 2 pi of 5 to the theta times the square root of 1 plus the natural log of 5 squared. But that's just a number, so I just have to integrate 5 to the theta, so that's equal to 5 to the theta divided by the natural log of 5 times the square root of 1 plus the natural log of 5 squared. And actually, oh no, just the natural log of 5 is squared. So I can't pull that out from underneath the radical. I do need those parentheses, and I need more parentheses. There we go. There we go. Okay. Evaluated from 0 to 2 pi. So I have 5 to the 2 pi over natural log of 5. And this is a constant multiple, so just to save me from writing, I'm going to pull it out and have the square root of 1 plus natural log of 5 squared, all of that over the natural log of 5 times 5 to the 2 pi minus 5 to the 0 power, which is 1. That is an exact answer. Phew. Okay. These three, we're going to find the length of the curve, correct to 4 decimal places. So try those on your own. You get to just plug those into your calculator. Okay, so for part A, it was easy. I got 16. Just memorize these formulas. R, dr d theta, square root, sum squared. R was tangent, dr d theta was secant squared. That one, your limits of integration were given to you for B. For C, you had to know that sine of 3 theta is a 3-petaled rose, and it only takes the interval from 0 to pi to create that. So, practice these. You can do it. We got one more section to go. The last part of this section is all about finding tangent lines and finding where tangent lines are horizontal or vertical. We need to find a derivative. We do it exactly the same way as we did for parametric. We rewrite x is r cosine theta, y is r sine theta. So dy dx would be equal to dy d theta. So r primed times sine of theta plus r times the derivative of cosine, the derivative of sine, which is cosine, product rule, r primed cosine theta for dx d theta. I'm going to go ahead and put minus because I know the derivative of cosine is negative sine, so minus r sine theta. If we want to know where the horizontal tangents are, just like with our parametric equation, horizontal tangents happen when dy d theta is equal to 0, as long as dx d theta is not. Vertical happen when dx d theta is equal to 0, when you have undefined slope. So, example 5. For the cardioid, find the slope of the tangent line when theta is equal to pi over 3. So, r is 1 plus sine theta. I like to go ahead and write down what r primed is. R primed is cosine of theta. So for part A, first thing I need is dy dx, and I start with, I like to go ahead and write down my x and y every time, just so I have it there for handy reference. So x is equal to r cosine theta, y is equal to r sine theta. Yeah, I know it was at the top of the page, but I write it down every time I do a problem because it helps me to remember that dy dx is equal to r primed, which would be cosine of theta, times sine of theta, plus r, which is 1 plus sine of theta, times the derivative of sine, which is cosine theta. Living on top of r primed cosine of theta times cosine theta minus r times sine, because the derivative of cosine is negative sine. So for part A, you don't have to simplify this. You could just go ahead and plug in pi thirds if you wanted to and find the slope of that tangent line. So dy dx when theta is equal to pi thirds would be equal to cosine of pi over 3, which is 1/2 times sine of pi over 3, plus 1 plus square root of 3 over 2 times 1/2. All of that divided by cosine of theta, pi over 3, times cosine, minus 1 plus square root of 3 over 2 times square root of 3 over 2. Well, let's do some arithmetic. So I have square root of 3 over 4 plus 1/2 plus square root of 3 over 4. I just multiplied, and then I distributed. Down below I have 1/4 minus square root of 3 over 2 minus square root of 3 times square root of 3 gives me 3 over 4. So looks like I have on top, I'll go ahead and simplify the top. I have square root of 3 over 4 plus square root of 3 over 4, which gives me 2 times the square root of 3 over 4, which is the square root of 3 over 2, so it gives me 1 plus square root of 3 over 2. So square root of 3 over 4 plus square root of 3 over 4 plus 1/2 is 2 times the square root of 3 over 4 plus 1/2, which is square root of 3 over 2, plus 1/2, which is 1 plus the square root of 3, all of that divided by 2. Similarly, down below, I have negative 3 over 4 and 1/4. That gives me minus 2 over 4 minus square root of 3 over 2, which would be minus 1/2 minus square root of 3 over 2. So I have minus 1 minus square root of 3 over 2. And I'm going to just kind of block this off here because that's just kind of my scribble work. Well, I have over 2 over 2. This is the same thing as 1 plus square root of 3 divided by the negative of 1 plus square root of 3. I did a lot of work to get minus 1. Now, just because you might be asked to do this on a WebAssign or perhaps a test, I don't know. What if you needed the equation of the tangent line? At theta equals pi over 3. Then you would need to figure out x, which is equal to r cosine theta, which x at pi over 3 would be equal to 1 plus sine of pi over 3 times cosine of pi over 3, which would be equal to 1 plus square root of 3 over 2 times 1/2. 1/2 plus square root of 3 over 4. And then y would be equal to r sine theta, which would be 1 plus sine of pi thirds times sine of pi thirds, which would be equal to 1 plus square root of 3 over 2 times square root of 3 over 2, which would be square root of 3 over 2 plus 3/4. So y minus my y coordinate is equal to slope -1 times x minus my x coordinate. So if you needed the equation of the tangent line, it's not hard. Once you have the derivative, just be sure you get your x and your y. Now to move on to part B, I just copied down dy d theta from my other page, and I need to set this equal to 0. So first I need to get rid of that set of parentheses. 0 is equal to cosine theta sine theta plus cosine theta plus sine theta cosine theta, but cosine theta sine theta is the same thing as sine theta cosine theta, so I really have 2 cosine theta times sine theta plus cosine theta. And since I'm setting this equal to 0, let's factor out a cosine of theta. I have 2 sine theta plus 1. So either cosine of theta is equal to 0, which means theta is equal to pi over 2 or 3 pi over 2. We don't have to find all the solutions, only the ones between 0 and 2 pi, because that's what it takes to draw that cardioid. Or 2 sine theta plus 1 equals 0. So 2 sine theta is minus 1. So sine of theta is minus a half. So I know theta has 6's in its denominator, and I know sine is negative, so it has to be 7 pi over 6 and 11 pi over 6. So if none of the denominators are equal to 0, then we're good to go, and we know exactly what our answers are. Let's set that denominator equal to 0. I'm going to pause and get a new sheet of paper for that. Just to save myself from rewriting stuff, I went ahead and made that cosine squared and distributed the sine and got minus sine theta and minus sine squared theta. I need to set this equal to 0. So I'm going to replace this cosine squared with 1 minus sine squared of theta minus sine of theta minus sine squared of theta, because I need a equation that only has sines in it, so I got rid of this cosine. So this leaves me with 1 minus sine of theta minus 2 sine squared theta. And I'm really not a fan of having that leading coefficient be negative, so I'm going to rewrite this as 2 sine squared theta plus sine of theta minus 1, because those have the exact same solutions. I just multiplied both sides by negative 1. So 0 is equal to 2 sine theta. I know I have a 1 and a 1. I need this to be plus, so I put the plus here and the minus there. That way when I do inners and outers, I get plus 1. So 2 sine theta minus 1 equals 0. So 2 sine theta is equal to 1. Sine theta is 1/2. So theta is equal to pi over 6, or 5 pi over 6, the positive things with 6 in the denominator. And then we have sine of theta equals negative 1, so theta equals 3 pi halves. And now is the problem child, because it's a 0 of the numerator and the denominator. So let's sketch this graph and see what it looks like. We have theta, and our function is 1 plus sine theta. So 0, pi halves, pi, 3 pi halves. If I plug 0 in, I get 1, 2, 1, 0. So 1, 2, 1, 0, very much not to scale. But it looks something like this. And I can see that I have a horizontal tangent there at pi halves. I have a horizontal tangent here at negative 7 pi over 6 and at 11 pi over 6. I have vertical tangents. Yeah, my picture's not perfect, but we can pretend that they're at 5 pi over 6 and at pi over 6. And I can see that here at the pole, when theta is equal to 3 pi halves, I have a vertical tangent. The vertical overwhelms the horizontal. Now, the way you would prove that would be to look at the limit as theta approaches 3 pi halves of the entire derivative which we have written up here, and I'm just going to show you where we did that. Yeah, solution, the easy part, here's the harder part. So, when theta is 3 pi over 2, both dy d theta and dx d theta are 0. So we look at the limit as x approaches from the right or from the left. Using L'Hopital's rule, we end up with infinity. So I'm okay with you looking at the picture and telling me, I can tell by the graph, that the tangent line there is vertical. The derivative does not exist there. Okay, try this one on your own. Find the slope of the tangent line to the given polar curve at the point specified by the value of theta. Easy. Find the derivative, plug in pi over 4. Go. This is what I got. So I just wrote down x is r cosine theta, y is r sine theta. I wrote down r primed. I wrote down r. So r primed sine of theta plus r cosine theta. R primed cosine theta minus r sine theta. Then I plugged in pi over 4. And since cosine and sine are both square root of 2 over 2, it was really easy to plug it in. And then, because I never trust myself, I went ahead and put it in Desmos. And just so I didn't have to type stuff in, I made another function for f of x so I could plug pi over 4 into my r and do sine of pi over 4. So this is my y coordinate when theta is equal to pi over 4. You can see right here. And here is my x coordinate. So I have y minus my y coordinate is equal to slope times x minus my x coordinate. And yeah, it actually is the tangent line, the slope of the tangent line there. Okay, let's find some horizontal and vertical tangents for r equals sine of theta. You give it a try, and I'll see if I can get my cat to help me give it a try. So I wrote down my sine. R is sine of theta, then r primed was cosine of theta. X is r cosine, y is r sine. I set my numerator equal to 0, and I remembered that this is a circle that lives above the axis, and I only have to find answers that are in the period from 0 to pi because that's what it takes to draw this graph. And then I took the denominator, set it equal to 0 to find where it's vertical. She wasn't much help, but I still got it done. And then I did 1 minus 2 sine squared is equal to 0. I ended up with sine squared as 1/2. So I have horizontal tangents at 0 and pi halves. And I have, yes, at 0 and pi halves. And I have vertical tangents at pi over 4 and 3 pi over 4. So let's look at the picture. I added a little slider here, so I could see when theta is equal to pi halves, I have a horizontal. At 0, I have a horizontal. At pi over 4, I have a vertical tangent. At pi over 2, I have a horizontal tangent. 3 pi over 4, vertical tangent. So it's exactly what we expected. So there was a lot in this section. So don't be overwhelmed. Take it piece by piece. Practice it. And you can do this.